All right, physicists, welcome to our plague edition of physics. I guess not plague, more like extreme weather. So I know everyone has had a very tough week of it. I am sorry to hear about this. You'll notice that things are even getting a little rough at my place. I'm now in my overcoat, a little chilly here. All right, so this video should not have new stuff in it. It should all be going over problems to try to remind you of the quiz and to try to help you with your homework. So let's say you're a super confident person and say, I've got this all handled. I know all the stuff for the quiz. I have my homework done already. This might be a video to skip. On the other hand, I do a lot of problems that are relevant. So if you're at all confused about the stuff that we did on Monday, this might be a good sort of refresher video to sort of sand the rough edges off. So this is our first slide from Monday, where we worked on our first our three laws of Newton. On the quiz, there's a lot of Newton's third law stuff because I could only put stuff from Monday and last Friday on there. So there's stuff about, if a cantaloupe falls to the earth, the cantaloupe pulls on the earth and the earth pulls on the cantaloupe, and the forces are the same. So that's Newton's third law. Newton's second law is everywhere because that's your F net equals ma. And we will go over several examples of this today because this is really the whole unit. F equals ma. I, in fact, knew a guy in Arizona, this is a true story, who got a knuckle tattoo of F equals ma. So you gave him a fist bump and he'd give you an F equals ma, putting some force on you. Okay, and then the first law is just saying that if you don't have any forces acting on you, you'll either stay still or keep moving straight without changing speed. Okay, so in the homework that's due this coming Monday, I did give you a couple of problems just applying your F equals ma. And this one is, this problem is designed to remind you what it means when it says F net equals ma. And F net means that you just have to add up all the forces beforehand. So in this problem, problem 82 from chapter 5, it says, in the overhead view of figure 565, 5 forces pull on a box of mass 4 kilogram. Okay, so they're giving us the mass. The force and the magnitudes are 11 newtons for mass for force 1, 17 newtons for F2, F3 is going to be 3 newtons, F4 is going to be 14 newtons, and that's the one that's up at an angle, and F5 is going to be 5 newtons. And they give us the angle is 30 degrees there. Find the box's acceleration in unit vector notation and as a magnitude and an angle relative to the positive direction of the x-axis. All right, so this is just an F equals ma and vectors problem. Now, F net means you have to add together all the forces beforehand. But those of you who remember our vectors know that you can't just add these numbers together. You have to put them into vector form first. So I'm going to have F1, which is going to have an x component and a y component. F2, which is going to have an x component and a y component. F3, F4, and F5. Okay, so I'm going to get you started on this problem. I'm not going to do the whole thing. The way I'm going to get my net force in vector form is that I'm going to add up all the x's and add up all the y's, and that'll give me my f as a vector. Then the way that you get your acceleration vector is to take whatever your x component was divided by the mass, and then whatever your y component was and divide it by the mass. And then once you have that, you can find the size of it by using your Pythagorean theorem, ax squared plus ay squared, and then take the square root. And then your angle, you're going to have to use trigonometry. So for instance, in this case, F1 is pulling to the left, so that's in the minus x direction. So F1 would be minus 11, and then the y component would be 0. F2 is pointing in the minus y direction, and it has a size of 17, so that would be minus 17 and 0, because it's not pointing at all along the x direction. Okay, and these are all, of course, they're going to be in newtons, and then your F net is also going to be in newtons. You can do the rest of these. The one that is at an angle, of course, that's at an angle of 30 degrees. That one's going to be F4, I believe. So that one's going to be 14 cosine of 30 degrees for the x component, and then 14 sine of 30. That'll be your y component. I'm going to let you try to figure out what the other two are. Then you're going to add all the x components, add all the y components, find your acceleration, find a magnitude, and find an angle. Okay, so that is a standard problem. I am sure that when I give you the test, you're going to have some variation on this. All right, then on Monday, I gave you a very long video, probably the longest I've given you so far, 55 minutes. And it involved two new ideas. One was the idea of frictional forces. And for frictional forces, we developed a model for which the frictional forces depend only on the normal force of the block on the surface. And so there's a lot of other variables that turn out don't seem to have much effect. Like you could imagine that it might be the amount of surface area of the object resting on the surface that would determine the amount of frictional force, or you know, something else like that. It appears that it's just the normal force that determines your frictional force. So remember also we had two forms of friction. One of them was static friction, and this gave you a maximum value of static friction, how much you could maximally push on it and get that amount of force back without breaking the temporary, cold welds that the object and the surface have. So this coefficient of friction, this mu s or mu k, this is for static friction and kinetic friction. In those cases, it doesn't have any units because we have a force over here and a force over here, and this is just providing the proportionality constant. And remember that mu s is typically bigger than mu k. So for these, we usually have to have a two-step process in this type of a problem. One step where we write down the forces in the x and the y direction and solve for the normal force, and then with that normal force we find the force of friction, and then once we have that, we can figure out what our net force is and what kind of acceleration we have. Okay, so we're going to do a couple example problems with that again today to make sure that we feel okay with that. And then the other side is our centripetal forces, and centripetal forces are net forces. So remember, net force is not another type of force, the way that we've developed like gravitational forces and tension forces and normal forces and frictional forces. these are the types of forces that we're using to, tell stories in this unit. Centripetal force is not an extra force. It's a way that those forces that we already have are being used. And it's just any force that directs the motion towards the center of the circle. And we already developed what the centripetal acceleration is, and just using F equals ma. If we have the centripetal force is going to have a size dependent on the magnitude of the centripetal acceleration. And so there's your mass times v squared over r. Okay, so an example that I gave you in the homework is a Ferris wheel. We'll do that problem today. Another great example is that of the moon going around the Earth, or the Earth going around the sun, or anything about that. They approximate circular motion. All right, so here's a good practice homework problem with frictional forces. Hopefully you have tried this, and as I said, if you already know how to do this problem, you can always fast forward a bit. Okay, so we have a 3.5 kilogram block. So mass is 3.5 kilogram. Pushed along a horizontal by a force of magnitude F, pushing 15 newtons. Now, the thing I want you to notice right off the bat, and this is at 40 degrees, is that this force is the one that might make this problem just a little bit complicated, because it pushes part of its force in the x direction. If we set up our xy like this, part of that force is in the x direction. In fact, the part that's going to be in the x direction is going to be 15 newtons times cosine of 40, and then it's going to be partially in the y direction. And notice that it's pushing down, so it's going to be minus 15 newtons times sine of 40. For those of you who like the, just blindly using the sine and cosine, remember that you can always put this in terms of a 360 degree circle, and so that would be angle of 320 degrees. Okay, now what other forces do we have here? Just looking at this rationally, it seems like I'm going to have mg, my force of gravity. I'm going to have a normal force, and just looking at this as a person who's done a lot of these problems, I know that because the normal force has to counteract both the force of gravity pushing down and part of this this applied force pushing down. You can imagine there's a burly guy really putting his back into it and leaning forward on it like this. So in that case, the normal force is actually going to have to be bigger than mg for this particular problem. And then you have some force of friction going back like this. And if I'm able to move, or if I'm able to accelerate, I should expect that this force of friction is either going to be bigger, or it's going to be smaller, or at most equal to that. Okay. So it's pushed along a horizontal floor by the force F of magnitude 15 newtons at an angle of 40 degrees with the horizontal. The coefficient of kinetic friction between the block and the floor is 0.25. So mu k is 0.25. Calculate the magnitudes of the frictional force on the block from the floor and the block's acceleration. Okay. So the block is moving. That means that we have a constant amount of frictional force from our model, because the frictional force that we should expect is going to be mu k times the normal force. Okay, so what do we have to do here? We have to add up our forces in the y direction to find our normal force, and then that'll give us our force of friction. Okay, so if I'm looking at this now, my forces in the y direction are going to be my normal force pushing up minus the y part of the force being applied, so minus 15 newtons times sine of 40. And then I'm going to have also my mg pushing down equals 0. Okay, so what you're going to do there is you're going to use all this. You know what mass is, you know that g is 9.8, and you can find out what your Fn is. You know your coefficient of kinetic friction, and you can find the force of friction. Okay, so that does part A for you. For part B, you can go ahead and find the block's acceleration. Well, the acceleration is going to be in this x direction because we're pushing it along this surface. So what do? We're going to once again use Newton's second law, F equals ma. But now we're going to go, what are the forces in the x direction? Well, I have this 15 newtons times cosine 40. And then I have a minus the force of friction equals m times a. And ta-da, that's what you're going to solve for. You're going to solve for a. You know what m is, 3.5 kilograms. You've found the force of friction in the previous part of the problem, and this is just a number. Okay, so in part A, you calculated the frictional force in newtons, and then in part B, you calculated the acceleration in meters per second squared. Okay, so those are the two basic ideas of this week. Oh, something to keep in mind, it is Friday, so it's quiz day. Let's do a quick problem. A bicycle racer is traveling at a constant speed v around a circular track. The centripetal acceleration of the bicycle is ac. Now, I want you to remember AC equals v squared over r, where r is the radius of the track and v is the speed that the cyclist takes going around. What's our question? What happens to the centripetal acceleration of the bike when the speed is doubled to 2v? Okay, let's try it. If we go here, we can say 2v squared over r equals 2 squared, 4v squared over r. But that's just my original centripetal acceleration, so that would be 4 times that original AC. Okay, there we go. We've got our answer. Now, in your PowerPoint for today, I did give you a problem that is a slightly harder version of the same thing. If you want to challenge yourself, I recommend going to take a look at that. I give you the answer, but I think it's a good practice to try to see if you can answer all of the versions, because they want you to look at what happens when you change the period, what happens when you increase the radius, what happens when you decrease the radius. So if you understand everything in that problem, you should be pretty solid on this. Okay, well, in this problem, we went through a version of this. In this one, instead of having someone pushing down, they're having someone pull up at an angle. And it says, a block is pulled at a constant speed along a rough level surface by a rope that makes an angle theta with respect to the horizontal. The applied force along the rope is F pull. The force of kinetic friction between the block and the surface is F. This says normal, it should be F friction. Okay, I will change that in the PowerPoint. Which one of the following actions will increase the frictional force on the block? Okay, well, what increases the frictional force? If I want to increase the frictional force, I have to increase the normal force. So let's think. Does increasing the angle made by the rope increase the normal force? Well, in this problem, the forces in my up and down direction are my gravitational force, the y component of that pull, and the normal force. So this normal force plus this F sine theta times are adding together to counteract my force of gravity. So if I increase the angle, if I increase that angle, I am going to be increasing the amount of force that's going to be in my y direction. So that definitely is not going to increase my normal force, nor is it going to increase my force of friction. Decreasing the speed of the block. Well, as long as my block is moving, I don't have a dependence on speed. Decreasing the contact surface area. Again, it doesn't appear in my model, so it doesn't matter. Increasing contact surface area. Again, it makes sense, but it doesn't appear in my model, so let's nix it off. Increasing the weight of the block. If I increase the weight of the block, I increase the force of gravity, and hence I would need to increase the normal force for it to counteract the force of gravity along with this upward pull from the tension. Okay? So that's how you would look at a problem like this. I did give you here's a slightly harder version of this that I don't think would be fair to put on a quiz. It might be fair for a test. I don't know. It's a classic problem. In fact, when I was an undergrad, I did this as a lab. I don't know if Dr. Golov is going to have you do this as a lab or not. Here's the idea. It says a brick is resting on the surface of a flat board. One end of the board is slowly raised. The brick begins sliding down the board when it makes an angle of theta with respect to the board's horizontal plane. Which one of the following gives the correct expression of the coefficient of kinetic friction in this situation? Well, what is this situation? In this situation, I just have the force of gravity. I have my normal force. And I have my frictional force. And those are my only three forces that I have to worry about. However, as we did last week, in this type of a problem, you basically have a screwed up coordinate frame where your y and your x are tilted. And so for your normal force to cancel out the gravitational force, it only has to cancel out the part of the gravitational force that's perpendicular to the surface. So this would be mg cosine of theta. So your normal force that's canceling that out has to have also a magnitude of mg cosine of theta. And therefore, your maximum static friction is going to be mu s times mg cosine of theta, because it's the coefficient of static friction times the normal force. And then if you say that the FF minus mg cosine of theta equals 0, because in this case you are going ahead and saying that's the absolute limit that my frictional force can apply and not have this block slip, you can go ahead and stick this into that and say mu s times mg cosine whoops. This force in the x direction should be mg sine theta. So this was your y direction. This is your x direction. So my force of friction is mu s times mg cosine theta minus, I messed up again, sine theta. This is mg sine theta. So force of friction is cosine theta, and then the force of gravity in the minus x direction is going to be mg sine theta. Okay, and then you can go on from here to solve it by dividing everything by m. You can divide everything by g. 0 divided by g is still 0. And then you can find that mu s equals sine theta over cosine theta, which is in fact the same as tangent of theta. Okay, so that would be a hard problem, but still following from all of the principles of stuff we've done so far. Oh, all right. So here's a last homework or last quiz type question. I hope you noticed these questions that we do during lecture are a little harder than the actual quiz questions. I'm not trying to punish you with these quizzes. Okay, so here's another example that brings together our two topics of the week: frictional forces and centripetal forces. Rancher puts a hay bale into the back of her SUV. Later, she drives around an unbanked curve with a radius of 48 meters. At a speed of 16 meters per second. So V equals 16 meters per second. What is the minimum coefficient of static friction for the hay bale on the floor of the SUV so that the hay bale does not slide while on the curve? Okay, well, we're told that let's write down a few things. Our normal force minus whatever the mass of her SUV and the Rancher is, let's just call that big M times G equals 0. So that's your y direction equation. In your x direction, you can write down that your force of friction basically is going to equal your centripetal force, okay? And so that's going to be M times V squared over R. Okay, so this is me saying, just identifying and saying, in my x direction, I only have that frictional force, and so how big is it going to be? It's just going to be mv squared over r. Now, this frictional force is also going to be mu times F normal is mv squared over r. And notice in this case, my F normal is just going to be mg, so I can stick in m times g equals mv squared over r. So the reason I'm able to solve this problem is because I have an m on both sides. I can divide by m on both sides. And I can go ahead and find that mu equals v squared over g over r. Okay? So you can check it out. You can stick in the numbers. I believe that the answer is 0.33. The thing to notice here is that you have meters squared over seconds squared on the top, and this is meters per second squared times meters. So this is also going to be meters squared over seconds squared on the bottom. So it does have the correct dimensions for just a ratio. It doesn't have any units. Okay, as I said, this should be a short video. So this is the last thing that I'm going to go over. This is a homework problem that you have in your homework that's due this coming Monday. Let's take a look at it. This is one of those types of tricky ones, but it's not tricky because the math is hard. It's tricky because it forces you to think your way through the problem. Okay, it says a student of weight 667 newtons rides a steadily rotating Ferris wheel. At the highest point, the magnitude of the normal force on the student is 556 newtons. Okay, so here's the story. At the top and at the bottom, the force up is going to be the normal force that's going to be acting on the student. The force down is going to be the gravitational force that's acting on the student. And at the bottom, you also have a normal force, and you also have a gravitational force. But those aren't going to be the same normal forces at the top and bottom. Why? Well, because in this case, the normal force and the gravitational force do not cancel out. The normal force is pushing up, the gravitational force is going to be pulling down, but when you're at the centripetal force always has to be pointing towards the center of the circle. So, when you're at the bottom of the circle, the centripetal force is pointing up. When you're at the top of the circle, the centripetal force is going to be pointing down. Therefore, at the top of the circle, we should expect the normal force to be smaller than the force of gravity. At the bottom, you should expect it to be bigger than the force of gravity, such that at the top, you have a net force pointing down. At the bottom, you have a net force pointing up. Now, that's what we see here. We are given that the student has a weight of 667 newtons. And in this case, the force of gravity is stronger than the normal force. Part A asks, does the student feel light or heavy there? Okay, well, you can use a little bit of personal experience. You probably have been in a car where the car is sailing over a hill, and then as it goes down really fast, your stomach feels like it's kind of coming up. You feel light. So the student at the top of the Ferris wheel feels light. Why does she feel light? Well, the answer is that the real weight that you feel of yourself is actually the weight of the normal force. If you felt less normal force pushing up on your butt when you're sitting in a chair, you would feel lighter than you do. And so in this case, because the normal force pushing up is lesser than the force of gravity pulling down, she feels light. Now, something to realize is that your centripetal force is going to be that net force. So it's going to be Fn minus Fg. So the centripetal force is going to be 556 newtons minus 667 newtons equals minus 111 newtons. So the reason that you get a minus on there is because that force is pointing down. Now, part B asks, what is the magnitude of the normal force at the lowest point? It should say Fn. I'm going to have to edit this a bit. Okay, well, again, you have the centripetal force equals Fn minus Fg. But in this case, the centripetal force which is the same as the net force. It's just a particular way the net force is being used. It's pushing towards the center of the circle. So what direction is that? That should be up. So for our centripetal force here, we're going to put a plus 111 newtons. The weight, which is the force of gravity, is going to be the same, Fn minus 667 newtons. All right, so I'll let you do the short algebra there. Okay, part C and D ask, what is the magnitude if the speed is doubled? What is the magnitude Fn at the highest and lowest point? Okay. Well, this is sort of similar to a problem that we did earlier. If you have 2 times the speed, okay, your centripetal force is F equals ma beforehand, which is actually v squared over r. If you go ahead and change this to have 2v, you're going to have m times 2v squared over r, m, which is going to be m times 4 times v squared over r. So this is, in fact, your force has gone to 4 times the force. So in each of these problems, what you would do is, instead of using that 111 newtons, you would go ahead and use, so for part C, for instance, at the highest point, you would use negative 444 newtons. And then this Fn is unknown, and the gravitational force, the weight, would still be just 667 newtons. And then at the bottom, it would be a positive 444 because the direction of that force would still be towards the center of the circle, even if the speed is doubled. Okay, so I've basically done that problem. I'll let you finish up the last bits. Okay, so that's basically all I'm doing. If you have questions, I will be around all day, so just hit me up, and I'm happy to hop on Zoom and just work a couple problems with you. By the way, today, when I'm recording this on Thursday, or yesterday if you're watching this on Friday, we had another rover land on the moon, so that's very exciting, and we'll start seeing some cool images. And I just bring it up as one of our nice examples of physics in action, and also the United States really getting something right and crushing it. Okay, so what are our big ideas of today? None really, because all of the stuff that I've talked about is stuff that I should have covered on Monday. I do want to get across, of course, that we have a quiz that I want you to try that's due at midnight on Friday night, and I also want to encourage you to work on your homework. If you have any questions, please email me. And of course, the other ideas are the old ones. The sum of all the external forces on an object cause it to accelerate via Newton's second law, so F equals ma. I'm not going to tell you that you get extra credit if you get that tattooed on your knuckles. No, I'm not. Okay, frictional forces oppose the direction of motion on an object's frictional forces oppose the direction of an object's motion proportional to the normal force. Okay, I agree with that. That's your F of friction equals mu times F normal. So it doesn't depend on, for instance, the size of the surface of the two surfaces that are touching. It only depends on the normal force. And then centripetal force is an example of a net force. So it's not a separate type of force. It is a net force. That's just the sum of, for instance, your frictional force or your normal force and your gravitation. But the key thing about it is that centripetal force, which is m times v squared over r, that is always directed towards the center of a circle. Okay, so thank you for watching. Please hit me up if you want to work some problems over Zoom. I will be available during class time or anytime during the afternoon.